So the main focus of my research is indeed on the next generation of the photovoltaics. And before I present a part of our achievements, I would like to give you a general motivation why we are interested in the solar energy at all. Because we are receiving over 23,000 terawatt year per year power from sun just on the emerged continents, which is dwarfing all other classical and renewable sources, and also it's more than 1,000 times bigger than the global average power consumption. So we are talking about the most abundant renewable energy source. But when we are looking to what we have done so far, just around 5% of our world consumption, power consumption, is based on the renewable sources altogether. And out of that, the solar energy has just a share of around 1.25%. So we are far behind the potential of this huge source. And our goal is to develop different type of the photovoltaic technologies as the most relevant technology for harvesting the solar energy to address different types of applications. The organic photovoltaics is one of those technologies that, because of its fantastic properties, has entered the market already in research phase. As you see here, they are colorful, they are semi-transparent, they are flexible, they are foam-free, and most importantly, they are printable. And when we are talking about printing and printing techniques, it means that we should end up with a low-cost product. However, still there are a few fundamental challenges in terms of the performance and the stability that has to be addressed to make the organic photovoltaics competitive with the well-established technologies like the silicon one. One of the main issues and challenges with OPVs is that they are based on the pi conjugated polymer and small molecules with the molecular excitonic natures. And it means when you excite an electron from the HOMO level to the LUMO level, they are forming a tightly bounded electron hole pair called exciton. And it's narrowing the absorption profile of our material compared to an ideal flat absorption like what silicon has. And it's reducing the short circuit current of the device, JC. The second point is that we need to introduce a second material with the higher electron affinity called acceptor to split this whole electron pair as the free charge carriers to be extracted at their corresponding electrodes and produce electricity. At the interface of these donor acceptor materials, new states are formed called charge transfer states that indeed cause some energetic losses and reduce the open circuit voltage in our devices. And this class of materials, organic materials, are kind of soft and amorphous materials. So they are trap dominant, and there are a lot of non-radiative recombination that, as you see here, they are reducing the open circuit voltage 2 to 4 times more than other technologies like silicon or gallium arsenide. And finally, the charge transport in this class of materials is based on the hopping process and very electric field dependent, and it limits the fill factor in our devices. So if we are going to boost the power conversion efficiency in organic solar cells, we have to go for parallel approaches to address any of those issues. And it's exactly what we were doing the time I was leading the organic photovoltaic team in Erlangen-Nuremberg University. We were working on the molecular design of different class of material to realize what should be the backbone, what should be the alkyl chain, how many of these pi conjugated bridge do we need, and so on. In addition to the material designs, we were working on the understanding the drying kinetic and the morphology control of our photoactive layer, this blend of donor and acceptor, to optimize that. And this photoactive layer is always sandwiched between the hole and electron transport interface layers and cathode and anode. So we need to put a lot of effort also on the device and interface engineering to modify them for the best extraction and the functionality. And for sure, to overcome this narrow absorption of our materials and the Schottky quasar limit, we need to go from a single junction to multi-junction or tandem structures, where we stack two materials with the complementary absorption on top of each other. However, this tandem structure are very complicated in terms of the optoelectrical optimization. Needs a lot of laboratorial efforts in the lab or a lot of simulation. And most importantly, if we think about the aim of our technology, which is printing in large area, then printing 10 to 15 layers on top of each other in the way that the top layer is not damaging the beneath layer is a huge challenge. So we were thinking, how do we can get the benefit of this structure, which is broader absorption profile, but stay with a simple single junction. And it was the time we started developing a new concept called Ternary Solar Cells, or also called Ternary Sensitization, where we introduced the second absorber or sensitizer with the complementary absorption profile to the host material of absorber 1 acceptor. So now we are dealing with a blend of three materials in a in our photoactive layer, and for sure we should understand what is the favorite energy level alignment between these three materials and how does it responds to the morphology, formation, and the device performance. But before answering these fundamental questions, it was our job to prove and demonstrate the potentiality of this concept. Does it make sense to put effort and time to optimize such a concept? Here you can see that when we start our work by introducing the low bandgap polymer called silicon PCPD TBT as a sensitizer to the host system of P3, the PCBM, how beautifully we can sensitize and extend the absorption to the near IR regime, where our host system, the red curve, is not absorbing at all by increasing the sensitizer content. And altogether, we were able to improve the device performance over 30%, which was a great news for our technology and our community, because we did nothing except adding a bit of the third material to the system, and it's getting 30% more efficient. And it's not just a matter of adding the third component. We can go for the higher number of the components, have multi-component sensitization and go from ternary to quaternary and so on, and still have the functional devices with the improved performance and extended absorption window. But it took really a couple of years to understand what's going on with the charge transfer and transport of these ternary systems and the complex morphology which is formed. One of the first mechanisms that we revealed was cascade charge transfer, where the energy level of our sensitizer is sitting between the energy level of our host donor and acceptor. And in this way, the produced charge carriers can have a cascade charge transfer. It's actually corresponding mainly for the morphology that the sensitizer is sitting at the interface of our host donor and acceptor. If the sensitizer is embedded in one of our host phases or get well intermixed with one of our host materials, then the energy transfer is the most corresponding mechanism for the charge transfer. And if the sensitizer is on its own enough good in packing and transport properties, then it can form its penetrating network and have a direct contribution in the charge transport, which is also called parallel like charge transfer. The next question to ask was, does ternary sensitization do more than just absorption extension and increasing the short circuit current? The answer was fortunately yes. We learned over time that we may have a significant improvement of fill factor or even the composition tunability of open circuit voltage by introducing the sensitizer. Here was quite easy to understand what's going on. So we have higher photon harvesting, and that's the reason we can improve the short circuit current. But honestly, that time it wasn't trivial to understand how introducing the third component can also improve the fill factor or open circuit voltage. As an example here, you can see that when we were introducing the same sensitizer, silicon PDTBT, to a high efficient host system of PTB7 PC7 TBM, we were gaining in the efficiency not just because of improved JC, but mainly because of a huge improvement in fill factor, a fill factor over 77%, which is still one of the highest reported fill factor for ternary systems. And our recombination study under the open circuit condition, open circuit voltage condition, showed that indeed, by introducing the sensitizer, we are reducing the trap-assisted monomolecular recombination in the system, which is relying on the fact that by a smart design of the ternary system, we let our charge carriers to be transferred from a amorphous trap-dominant host system like PTB7 to a higher order sensitizer with the narrower density of a state like silicon PCPD-TBT, and then when this highly ordered sensitizer starts to contribute in the transport, it can adjust the recombination mechanism and improve the fill factor significantly. And based on all these lessons that we learn how to design a full functional ternary systems over the time, we were able to make a new ternary systems with a high efficiency over 11%, importantly, at the roll-to-roll processing relevant thickness over 250 nanometer, because it's very important for printing technologies to have enough thick films. And this high efficiency encouraged us also to fabricate the modules. As you can see here, we were able to keep over 8% on the glass ITO substrates and around 7% also on the flexible PET IMI substrates in our modules. However, in addition to the performance improvement, very recently we have demonstrated that this ternary sensitization also can have a significant influence and improvement on the stability of our solar cells. Here you can see, for example, when we introduce any of those Fullerene derivatives as the ternary component to a host systems based on this benzodiazepine polymer blended in the very well-known non-Fullerene acceptor of IT4F, then we are improving significantly the photostability of our devices. Our comprehensive study showed that indeed what is happening is that this zinc oxide, the electron transport layer of zinc oxide, which is one of the most used whole transporting layer in OPVs and also very well known for its photocatalytic activities, is inducing some radicals in the photoactive layer, that those radicals can attack the vinyl bond of the non-Fullerene IT4F and damage that and degrade the system very fast, especially under the UV radiations. So when we are adding any of those Fullerene derivatives, especially the ICMA, they are acting as the radical scavengers and sacrificial agents to protect the photoactive layer from the photocatalytic activities of zinc oxide. And in this way, they can have a significant influence on the stability of our devices. So far, what I have presented for you, always we are talking about the host, organic host systems plus the organic sensitizer. But I was very interested also on the hybrid organic inorganic ternary cells, because we can have a combination of unique properties of both semiconductors, and also we can widen the range of organic electronics applications into the emerging technologies like near IR detectors or X-ray detectors, which are still relying mainly on the inorganic semiconductors. One of the biggest issues and challenges with the hybrid system is that when you introduce the inorganic quantum dots in high content into the organic host system, to have enough absorption and improvement in the device performance, they start to agglomerate and have a negative impact on the nanomorphology and the charge transport of our host system. So we were thinking to address this issue. We may fix the position of our quantum dots on a template like carbon nanotubes to avoid their agglomeration at the high concentration. And here you can see that how successfully this idea was working when we introduced our lead sulfide nano quantum dots on the carbon nanotubes. Then we were able to preserve the morphology and ordering of our host-rich PCBM on both pi-pi stacking and lamellar stacking direction, while introducing any of those components individually has a negative impact. And in this way, we were able to have a significant performance enhancement over 15% for our hybrid systems. So far, I hope that I could show you and convince you that we have developed a multifunctional concepts called ternary or multi-component sensitization, which is not just increasing the light harvesting and short circuit current, but also can adjust the recombination mechanism and improve the fill factor and open circuit voltage, and have a significant influence also on the stability of our devices, and led to the highly efficient and stable organic as well as hybrid solar cells and modules. And honestly, as a person spending over 6-7 years on the development of this concept, is my pleasure to see that nowadays this multi-component concept is the leading strategy in the organic photovoltaic technologies, and based on them we have over 18% efficiency, which is just great value and progress in this technology. However, in this between, a new technology also came up in the for the photovoltaic technologies called Perovskite solar cells, a crystalline material with the general structural formula of ABX3. And as you see here, this methyl ammonium lead iodide is one of the most reported, most efficient structure, perovskite structure for the photovoltaics. And in terms of the performance, as you see here on this roadmap, they are achieving over 25%, which is indeed comparable with the single crystalline silicon. So they are doing amazing in terms of the performance. However, we still have to address a few key issues to make them commercial. First of all, their poor photochemical stability. The second point is the printability in large area, since it's a polycrystalline materials, and for sure the presence of the lead and the toxicity is another issue that has to be addressed. The time that the community started to work on the development of the perovskite solar cells, we were trying also to transfer our knowledge on how to do from the organic photovoltaics to the perovskite photovoltaics, especially for the interface engineering based on different class of organic materials, and also the solar modules and tandem fabrications. One of the topics that is very active right now in my group is the defect passivations. As already mentioned, it's a crystalline material, and when we are processing that from solution in the room temperature, we are forming a polycrystalline film with a lot of defects on the surface and the grain boundaries. So what we are trying to do is to introduce the multiple ligand Lewis spaces to actually passivate these defects. One of them here as an example is this 110 phenanthroline, that you can see when we are introducing that on the surface of our Perovskite solar cell. We are completely changing the surface, and new platelets formation and form on this surface. Our high sensitive TEM characterization, actually analytical characterization, showed that what is formed on the surface has a completely different nature than a pure perovskite or a pure small molecule. Further investigation showed that what's happening is that adding this passivator, the electron lone pair of these nitrogen atoms is not just passivating the under-coordinated lead defects, but this passivator also can interact with the excess or unreacted lead iodide in the precursor and convert them that actually are harmful for the long-term stability of our devices to the beneficial mono or bis complexes of lead iodide 110Fen that can also facilitate the charge extraction at the interface. And in this way, we are not just improving the efficiency over 10%, we can stabilize also our solar cells, especially against the moisture and also the photothermal degradation issues. And now we are trying to make a rational design rules for the full functional passivators based on the pi conjugated organic materials to get a stability performance balance for the perovskite solar cells. In addition to the photovoltaics, we are also working on the next generation of the IR detectors, where the current technology is based on the epitaxial machine and ball soldering, very expensive and complex manufacturing. And in our startup called SERINO, we are working on the hybrid organic inorganic IR detectors, which is based on the inkjet printing. So we have much higher resolution and it's much more efficient in the cost, manufacturing cost. And since we are working with the quantum dots, indeed we can just tune the wavelengths for the detection and detection regime. Right now we are working on the pharmaceutical applications for the quality control of the medicines, but the technologies that we are developing can be also used for the breast cancer diagnosis or the portable sensors, CO2 sensors, and so on. Our startup have received several awards so far, and one of the last one is the one from Medical Valley that we received just in 2020. With that, I would like to sum up that what we are doing is working on the fundamental issues like the photophysics, charge transport, and nanomorphology of different novel, high efficient and stable and importantly solution processable materials to address the fundamental issues and then work on their processing issues for the roll-to-roll printing and the reliability and yield of our materials and information. And we are trying to have the interface engineering, device module design, and semi-transparency for different type of applications like the photovoltaics, photodetectors, and X-ray detectors, with a focus on the photovoltaic technology. In terms of the materials, as already presented and mentioned, we are working on the pi conjugated organic materials, hybrid organic inorganic systems, perovskite and carbon allotropies. And this research gives us a great opportunity for the large collaboration. And with that, I would like to thank all the people that had a contribution in this research and results, especially my previous host institutes and all my PhD postdocs, all the collaborators, and for sure financial support of these projects. And last but not least, thank you very much for your kind attention.